Start again. Our next speaker is Bruno Lindan, talking about limits via enrichment.
Cool. Thanks for having me. I'm Bruno. I'm a PhD student with Nicola Gambino here in Manchester. Okay, I'm going to set the scene first briefly. So there's a sort of general pattern scattered around a few different results in the literature involving taking, this should really be a sort of a kind of structure on a category C. So I'll give a couple of examples in a moment. And seemingly cleverly concocting something to enrich in so that when I in fact enrich in this base, I can recover the structure on C from just the fact of being a category enriched in WC. In some cases, possibly I need to ask for some enriched colimits in order to make this work. Okay. In fact, it's very good that we had to talk about operads first because one of the examples I have here, I think maybe this is the first one that I know of that fits this pattern, is that there's this base of enrichment. It's just a functor category. I'll tell you what P is in a second. So that at least a single object category enriched in it is exactly an operad, or maybe a symmetric operad. This thing P is just finite sets and bijections, or a skeleton of it, something like that. Another example, a fair bit more recent, but that's quite sort of similar in flavor, is this result of Richard Garner that if you take a very similar category, but instead of finite sets and bijections, I allow all maps between sets. And I enrich in this thing, then as long as I ask for some not too complicated enriched colimits, I get exactly categories having finite powers. Okay. I'm not going to say too much about the sort of general pattern because most of the talk is going to be about specific example. But I'll say a couple of things briefly here already as motivation. I mean, one is that these definitions are very, very compact, especially the first one. So, I mean, okay, finite powers, it's not too hard to write down what's going on there. But an operad is a fairly hefty definition. And this here is just one line. Now, obviously, it helps to have both handy, but it's still nice sometimes to be able to push all of the kind of axioms and coherence or whatever into the machinery of this base of enrichment. I also haven't told you where the monoidal structure comes about on these, but we'll see that later. So, okay, what we're going to be looking at today is a fairly mild extension of, I guess, that second example. So we're going to be taking categories with finite products and cooking up a base of enrichment so that we can get exactly categories of finite products as categories enriched in this thing with some colimits. And again, we need these absolute tensors cropping up, and we'll see some justification as to why that is. There's also a little bit extra that I'm really not going to talk about today. And this, yeah, so this is not, I would say, massively interesting on its own, although there is something at the end that I think is curious. This is mostly as a sort of warm up for a much more general thing that I'll only mention briefly at the end for a couple of reasons. I mean, one is that it's quite abstract and maybe a bit difficult to, I certainly found it much easier going through the sort of simpler case first, but also because it's not quite finished yet, it's work in progress. But I'll give a quick sketch of what's going on right at the end. One thing I'll say is that I no longer think this is a downside, but you might, if you're not familiar with enriching by categories, is that we're doing something a little bit more unusual. We're looking at enrichment in a by category, not in a monoidal category. So the plan for the talk is going to be to spend 10 minutes or so talking about enrichment in bicategories, how it differs from enriching in monoidal categories. I'll give you one example. We won't dwell on it for too long. And then we'll talk about the specific base of enrichment that we're going to be using to recover categories with finite products. And I should say as well, obviously, the interesting thing about the fact that you get categories with finite products as things enriched in this new base is that the limits involved become absolute. So I'll say a little bit more about that at the end. And then finally, just for a couple of minutes, I'll mention the sort of general patterns going on behind all of this. And I'll keep it quite light on the details, but if anyone heckles me at any point, I'll try and elaborate a little bit. So in terms of getting everyone up to speed on enriching in bi-categories, the differences are not too peculiar. So first of all, in both enrichment in a monoidal category and enrichment in a bi-category, we start with a set of objects. That's fine. Okay, but the main new thing that we have is a function from the objects of my enriched category to the objects of the base. And you usually refer to this as the extent of an object in C. So you can think of each object in C lying over an object in the base. Okay, and there's no equivalent piece of information for enrichment in a monoidal category. When you enrich a monoidal category, you have an object of V replacing the set of arrows from X to Y. But instead, because we have this new sort of fact that everything is lying over an object in the base, we have to take that into account. So the hom object becomes a hom one cell between the things that X and Y lie over. And there'll be a picture on the next slide as well. And similarly, we've got a hom two cell, sorry, a composition two cell between the composites of the hom arrows instead of a composition arrow between the tensor product of the hom objects. Okay, so it seems a little bit peculiar. Let's draw a quick picture. So maybe this is not, I don't know if you find this enlightening. Everything in C, you can picture lying over something in W. And in fact, if you like this kind of thing, it turns out that all of the information of being enriched in a bi-category can be packaged up quite neatly as a lax functor from the indiscrete category on the set of objects of the enriched category. Okay, so again, what that means is for each object in ob C, we choose an object of W. And for each, well, because it's the indiscrete category, that means we'll pick exactly one arrow from U to V if X is over U and Y is over V, and so forth. And also just to convince you that this is, well, okay, some of you probably know that every, a monoidal category is the same thing as a bi-category with one object. Just to quickly sketch how this works, if you start with a monoidal category, you can construct a bi-category with one object by taking the one cells to be the objects of V and then composition given by the tensor product in V. And it's fairly straightforward to see that enrichment in this bi-category is the same as enrichment in the original monoidal category. Okay. So just to summarize, we have this one new bit of information and everything else has been sort of promoted up one dimension. Excuse me. So if there's one thing to remember, just sort of bump up by one dimension everything that you already think about for enriching in a monoidal category. And usually the interesting examples come about when the base of enrichment looks something like relations or modules, maybe in some generalized sense. And I'll give you a very quick example. I think this is probably the first really interesting example of something you really wouldn't expect to be expressible as an enriched category in any way. And the idea is that taking a topological space X, I can construct a bi-category whose objects are the open sets of X and whose hom categories are the posets of subobjects of intersections. Which again, I said these things generally look a bit like relations. If you like, you can think about this as relations between U and V. These are subobjects of the product in this poset. And then it turns out that if you give me a sheaf on X, in the usual sense, there's a way to construct a category enriched in this thing that I've called WX here, although that's not traditional notation or anything. And the idea is that I'd start with a sheaf, which I've written as an ATAL bundle. And I get the WX category whose objects over U are sections over U. And okay, and then if I have an object over U and an object over V, I need a hom one cell from U to V. So that means it needs to be a sub-object of U intersect V, and it's going to be the collection of all points where the restrictions agree. Okay, this is really not at all relevant for the rest of the talk. I just wanted to give you an example of kind of how this works and convince you that you can get some sort of much more, things that you really wouldn't expect to turn up as like enriched categories. Very quickly as well, most of the theory you can do just pretty much exactly the same way, taking into account the changes. So you can define enriched functors. The one difference there is that a functor preserves the extent of an object. You can define modules. You can do weighted colimits. And if your base is nice enough, then you can define pre-sheaf and co-pre-sheaf categories. And briefly, what doesn't work as well, there are a couple of things that are a little bit pathological. So one thing is that we don't have an underlying category anymore. You have to be a bit more careful. If you pick an object in the base, you can just look at objects lying over that and get an underlying category of objects over W. But in general, there's no one category that plays in any reasonable sense the role of the underlying category of a W enriched category. And the other thing that doesn't work is there's no reasonable way to regard W as a W category, even if it's as nice as possible. So that means that even though I said you can do profunctors and pre-sheaves, you have to define them in, there's multiple equivalent ways for normal profunctors. Not all of them work because I can't say for pre-sheaves, I can't say arrows into W. Okay, so the main difference is this sort of extent phenomenon. And I'm going to try and get across just a little bit of the intuition, how we can use this to kind of encode algebraic structure on a category. So the idea is, I mentioned right at the beginning that we're interested in using certain enriched colimits to get okay, I just told you that there isn't an underlying category, but in a lot of cases, you only care about objects over a single thing in the base. So there's something that works pretty well. And you can use enriched tensors to get algebraic operations working as you want them to. Just briefly, again, I'm not going to recap the sort of exact definition of how tensors work in ordinary enriched category theory. But just to get a sort of type check what's going on, we're starting with an object so in this case, V is a monoidal category. I'm starting with an object in a V enriched category, and I'm picking an object of V, that's going to be the thing I tensor by, and I produce another object of C. And if you know about how weighted colimits work, then the definition is just there on the right. So the tensors are just a particular kind of weighted colimit where the shape is just the singleton. And I'm really not going to tell you about how weighted colimits work in general for enriching a bicategory. But in the case of tensors, it's at least, again, just to see the sort of the raw information that you need as input, it's pretty straightforward. So we're starting again with a W category C, remembering that every object in C lies over something in W. Okay, and now the weights, instead of objects of V, they're now going to be arrows in W. So if I take an arrow from U to V, and then the tensor of X by this arrow J is going to be an object over U that has a universal property that you can spell out in a similar way. And this delta V, delta U that I've written here, again, there's no longer just one singleton W category because everything lies over something. There's many of them. There's one for each object in the base. Okay. So the point is that if my W category C has tensors, or maybe just tensors in a certain class, so I pick a particular class of arrows in W and ask for tensors by all of those, then each such tensoring operation gives me a function from objects over V to objects over U. Okay. And the kind of the rough idea of how we want to cook up a base of enrichment so that today we're going to recover categories with finite products, but more generally with some kind of algebraic structure, is that I want the objects of my base to be like the arities involved. And I want to use these tensor products to encode the operation of taking objects of arity V to objects of arity U. So again, there is a kind of more uniform way of constructing these bases of enrichment. But even if we were just guessing, we would certainly want the example, the the base for the example we want to look at today, we would want its objects to look a bit like this. So we want to be taking finite products. So we want to be able to have something that takes as input something of arity n for n, a natural number. Again, it's not necessarily clear at this point that the objects over n are going to be n things in any particular reasonable sense. I'll say something about that later, but let's just say that they are. And then for each weight for finite products, we certainly want to have a one cell in the space of enrichment going from n to 1, because then tensoring by that is hopefully going to allow us to take some collection of n things and produce one thing that has the universal property of being the weighted product. Okay, so let me give you the actual definition of this base of enrichment. So the objects are going to be, just like I said, they're going to be, well, either natural numbers or finite discrete categories is maybe a more sensible way of thinking about this. And okay, maybe this is a bit peculiar, but the Hom category from M to N is going to be the category of functors from finite sets to the M into sets to the N. Really, I think to make things easier, we want to take a skeleton of finite sets here, but that doesn't really matter too much. Okay, at first sight, this isn't, it's not obvious how to make this into a bicategory. I don't know how to compose to such, something from M to N with something from N to whatever. One way to sort out the composition, the way to sort out the composition is to use the fact that functors from finite sets to the M is equivalent to functors from set to the M to set to the N, with the request that they preserve filtered colimits. So this, if I transport everything across this equivalence, I get things that I can actually compose and then transport back. And it turns out this lets you turn WFP into a bicategory. I'll just mention at this point, if you like this sort of thing, the more abstract way of setting this up is to start with the pseudomonad on cat, whose pseudoalgebras are categories with finite products. This happens to extend to a pseudomonad on the bicategory of profunctors. So that means that there's a new monad pseudomonad T prime that has the same action on objects and representable one cells as T did. Then this WFP is a bit of a mouthful. It's take the Kleisli bicategory of T prime, I restrict to the finite discrete categories, and I take the opposite. Okay, these two definitions are just exactly the same. I wouldn't focus too much on the abstract one for now, but it's there in case you wanted it. Okay, just to confirm one of the requirements, we baked in one of the requirements I said for this being a reasonable guess to check that the other one works as well. If you give me a weight, so a functor from n into finite sets, I ought to be able to get like I said, a one cell in WFP from n to 1, and there's a straightforward way of doing that, which is just to take the representable functor from finite sets to the n into sets. Equivalently, I've written that this functor category is also profunctors from 1 into finite sets to the n up, and just taking the representable profunctor corresponding to J. Okay. I thought I put this on there just in case anyone is not happy with weighted limits. I said products, and now I started talking about weights for products. In this case, it's very straightforward, and it kind of justifies the terminology pretty well as well. So if you start with a weight, so for each integer from 1 to n, a finite set, product weighted by that is exactly what you'd expect it to be. And I'll say as well, the kind of special thing about this bicategory WFP is that the right adjoints in this bicategory are exactly functors of the form on the right down here. So functors, these are, again, finite discrete categories on M and N objects respectively. So if I set M equal to 1, that's exactly what I've just been talking about up here. And I'll say a tiny bit more about this later on, but it turns out that this means that tensoring by anything of this form, the tensor by anything of this form is an absolute colimit in an absolute enriched colimit. Okay, so we've constructed this base of enrichment WFP, and I need to tell you if I'm going to have any hope of getting ultimately an equivalence between this here, which is the two categories with finite products, finite product preserving functors and natural transformations, and this thing here where I've asked for some suitable colimits. I'm going to start by telling you, if you give me a category with finite products, how do I construct a WFP enriched category? And again, I told you that because we want the objects in the base to behave like the sort of arities for the operations involved, then I certainly want the objects over n of gamma of C to be n many objects of C. Okay. And constructing the Hom arrow is a little bit more complicated, but really you should just think about this as telling me what how homming out of a product behaves in C. And this is, by the way, this is the sort of the way all of these sort of substitution monoidal structures work. Certainly the two I mentioned on the very first slide, the Hom objects, which now, because we're enriching in biocategories, the Hom arrows, always tell me how to Hom out of the operations involved. More explicitly, this Hom arrow is going to be the composite of these two profunctors, where there's a little x underlying is the extension of a functor from n into C to the free completion for finite products. But again, that's just there for completeness. It's not going to matter too much. And again, I've left out a lot of detail here. I haven't told you how to do this on 1 cells or 2 cells, but it all works out. It turns out that this thing, suppressed the fact that you have to check that this is a 2 functor, obviously, but once you've done that, it turns out that it's locally in equivalence. And then we go about the task of characterizing which WFP categories came from a category with finite products. And again, that's just in the way that I've mentioned is the sort of intended way to get products on the underlying. Okay, again, I said there's no underlying category. In this case, we only care about the objects over 1. So we're looking at the underlying category of objects over 1. And it turns out that if you start with a WFP enriched category and you request that it has, it's Cauchy complete, which means that it has all absolute colimits, then the underlying category of objects over 1 has finite products. And as you'd expect, this gamma of the underlying category of objects over 1 is what you started with. Okay, so that means that we have this equivalence that I mentioned was the sort of ultimate goal of this. And briefly, I'll mention here as well. Yeah, so I told you the Cauchy complete, if you don't know what this means, it means that it has all colimits that are preserved by any functor. Okay, I mentioned that these tensors that we're interested in, one such example. I should say, and I haven't written a slide on this because I didn't want to, bloat this too much with detail. But there's something that makes this a little bit subtle is the fact that because this base of enrichment is not biclosed, that means composition, in this case, post-composition doesn't have a right adjoint. I can't compose WFP modules. So I don't have a bicategory of WFP modules. I have a virtual double category. And those are the things that I want to use as weights for colimits. So you have to be a little bit, quite a bit more careful in checking that absolute colimits are what you want them to be, which in the usual setting are weights that have a right adjoint in modules. Here, it turns out that you need to ask for something a bit weaker than being a right adjoint. It's like only one of the 2 triangle identities is satisfied, which was curious, but it's not really relevant for what's happening here. So again, I'll just briefly, maybe this is overkill, but the point is that if you start with, as I was saying, just to summarize, you take a weight, so a functor from n to finite sets, regard it as an arrow from n to 1 in W, and tensoring by it tells you how to take the product of n things. And as I've already mentioned. So one curious thing about this is that it's turned the sort of property-like structure of having finite products on a category into just a property on WFP enriched categories. And again, I said right at the beginning that there was something extra as well, and I've hinted at it because the one problem is that if you just take an arbitrary WFP category, there's no guarantee that the objects over n, which essentially says that you can glue objects over one into an object over n. And the details of this really don't matter, but it turns out that you can do this and that the weights you get are absolute. And so if you ask for Cauchy complete WFP enriched categories, then this happens for free. And once you've got this, then the process of tensoring fairly straightforwardly gives you the right universal property in the underlying category of objects over one. Okay. I'll mention a little bit about where you can go with this. So first I said that there's a couple of maybe curious things you can do already just looking at limits. One is that really, again, a lot of the interesting stuff with finite products is kind of happening in the background and trying to make it as agnostic to the fact that I'm using finite products as possible. And it turns out that really the thing that makes it tick is the fact that if you have a functor that preserves finite products, then the extension to pre-sheaves also preserves finite products. And this is not true for any class of limits, but it's true for quite a lot of them, and it's called being a sound class of limits. Again, I want to be slightly cautious because there are a couple of details here that I still need to check, but the slide is work in progress. But one interesting thing that you can do is ask what happens when you take the co-complete WFP or whatever enriched categories. So here I've written for the equivalent construction where I started with finite limits instead of finite products. And what's curious about that is that you automatically get the underlying category of objects over one is co-complete, but it also has the sort of nice interaction between finite limits and co-limits that you get in what's called an infinitary pretopos. But a bit more, just to point to what I've sort of really been working on recently that generalizes this whole picture. The idea is instead of okay, we looked at a particular kind of structure on a category, we're going to instead start with a fairly arbitrary pseudomonad on cat, which just has to satisfy the one requirement that I can do this trick of extending it to profunctors. And I'll say as well, actually, you can go even more generally and just look at a pro-hour equipment, but okay, maybe really going a bit too far for now. Then I can look at categories enriched in the opposite of the Kleisli bicategory of the extended pseudomonad, and then construct a two-functor from pseudo-T algebras with lax morphisms into this thing. And again, with the same idea that the objects over a category X, say, are arrows from X into the algebra. And the expectation, once all of the details have been sorted out, is that you can, there's an equivalence between giving pseudo-algebra structure on C and certain colimits existing in the corresponding enriched category. So that's just an indication as to the sort of ultimate ambition of all of this. And I think, have I timed it well? I'm actually 2 minutes early, so I'm going to stop there for questions.
Okay, let's thank the speaker. Are there any questions or comments? Ivan?
So actually I have a lot of questions. Maybe so. First of all, the talk was super interesting. Thank you. So let me start with a first question. So there is a series of papers by Gardner where he proves theorems of this flavor for restriction categories, total functors, and F categories also. Does your framework, are you thinking of these examples?
I'm not aware of those examples, no. So I don't have much more to say than that I haven't read those papers.
Okay, then maybe we can talk. Maybe you can send me an email and I will send you the references. Okay. And then I have another question. From what I understand, you can cover the case of multi-categories, right?
Yes. That
Okay.
should fit into this, yes.
So then, have you seen the recent paper by Tarantino and Quentin Aristotle?
Yeah, so actually, I didn't want to dwell on this too much, but the main motivation for all of this was ultimately to get ultra categories to fit into this picture, because Richard
Okay.
Garner has a paper where he's conjectured something along these lines. And there's a small subtlety that the paper you mentioned, they construct only a skew monad extension to profunctors. But there's also, again, I didn't want to overload the last slide. There'll be a relative pseudomonad version of all of this, which I think should work out. But I don't want to say anything for sure at this point. But yeah, I have seen that, and that's
Cool.
that
Very,
should
very nice.
fit into this framework.
Thank you. Very cool.
Thank you.
Thanks. Raise this hand.
Hi, Bruno. Thanks for a very interesting talk. I enjoyed it a lot. I'm especially keen to see how this work in progress ends up in the end. I had a sort of a simple question, which is that sometimes when you enrich in a bicategory, when you look at the morphisms between enriched categories, they don't really give you what you want because of this extent preserving business. Whereas in your instance, this seems to be the right thing to ask for. Could you maybe comment on this at all?
Yeah, I could try. I mean, kind of with all of these bicategories, okay, let me stay on this particular example. Throughout, the only objects I care about are the ones over one. And ultimately, what I'm going to do is take the underlying category of objects over one. So the enriched functors will take an object over one to an object over one. And that's cool. In terms of what's going on with all of the other layers, those extra colimits that I mentioned briefly ensure, like I said, that objects over n correspond to n objects over one. And because those colimits are absolute, any enriched functor preserves them. So it takes objects over n to objects over n, but because they're secretly just tuples of n many things, it does exactly what you think it should do. So does that answer your question?
Yeah, that helps. Thank you.
Cool.
Okay, anyone else? If not, let's thank Bruno again. And I guess that's it.